Trig graphs, amplitude and period, algebra 2 trigonometry regions. All right, we're going to get our first look at some trig graphs today, mainly sine and cosine. We will be talking about some of the other trig graphs, tangent, secant, cosecant, and stuff like that. But today, your focus for this really is going to be about the characteristics of the general trig graph. But first, you need to kind of get to know what they look like. So this is the sine curve, and this is the cosine curve. Let me tell you a little bit about them, and first of all, show you that you can get this on your calculator. If you go to your calculator and type in y equals sine x. Now, what you need to do, though, is you can't just hit graph. You have to tell the calculator that you're doing a trig graph. So you have to hit the zoom button, and then number 7 is trig. So if you hit zoom 7, it will graph a trig graph for you. And this is the sine graph. Then, now, what this is doing is, first of all, let me point out a couple of things here. The y-axis is pretty standard. It just goes 1, 2, 3, 4, 5, and so on. But the x-axis is no longer really the x-axis. It is the theta axis. It's the angle axis. And so these intervals that we have marked here, now, they're in radians, because we tend to do that with trig graphs. But really, these are the quadrantal parts here, that this is 90. This is 180, this is 270, and 360, just in radian form. 0 is 0 even in radians. And the value of this sine curve, actually, we've talked a lot about this, believe it or not, because at 30 degrees, which would be about here, you're 1/2. And that is 1/2. That's halfway between 0 and 1. And then at 45 degrees, sine at 45, it's rad 2 over 2, but we know as a decimal that's 0.7, and so 0.7 would be, about there. And then at 60 degrees, we're rad 3 over 2, which is about 0.866, right? That'd be about 0.8 right there. So sine is increasing, and then sine 90 is 1. And a lot of it is, if you think back to the quadrantals, remember this is the point 1, 0, and then 0, 1, negative 1, 0, and 0, negative 1. And then also remember that sine is the y values of these coordinates, because x is cosine, sine is y. So at 0 degrees, at an angle of 0, which is here, we know that sine is 0. So that's why at 0, sine is 0. And then up at 90 degrees, sine is 1. At 180 degrees, sine is back at 0. That's right here. And then at 270 degrees, sine is negative 1. So that's down here. And then back at 360, when we finish our circle, we're back at 0. And so that's why sine is there. And it's very cyclical. So it's a wave that goes on and on and on. And our calculator graphs much more of the wave. You can manipulate the window on your graph if you want to see just a specific range or domain on your calculator. Like I can have it go from 0 to 360 if I want to get a picture similar to what I have here. I could also adjust the y scale to only go from 1 to 1 or 2 to 2. So by hitting the window button, you can play with the window features. The x minimum and maximum is, the angles you want here, and the y minimum and maximum is the up and down that you get for your graph there. So these values kind of should make sense based on what we know about sine 30, 45, 60. The other thing that I think is really worth pointing out is, remember that sine is y, and so sine is positive in quadrants 1 and 2 because of our whole ASTC thing. And it's positive in quadrant 1 because they're all positive in quadrant 2 because, again, it's the y value. But it's negative in quadrants 3 and 4. Well, quadrant 1 and 2... Excuse me one second. Sorry about that. Announcement came over the loudspeaker at St. John's right now. So anyways, what I was saying was that sine's positive in quadrants 1 and 2, but negative in 3 and 4. Quadrant 1 is between 0 and 90. And quadrant 2 is between 90 and 180. Notice that it's above the x-axis. It's positive. And then quadrant 3 between 180 and 270, In quadrant 4, between 270 and 360, sine is negative. So when sine's positive, it's above the axis, and when it's negative, it's below the axis. So it's positive in the first two quadrants, negative in the last two quadrants, which is kind of an interesting feature there. And then when we switch over to cosine, we know that cosine's positive in the first quadrant, and it's positive in the last quadrant. But cosine's negative in quadrants 2 and 3. So that's kind of why the cosine curve is what it is. And then also this idea that cosine, again, back to our quadrantals, at 0, it's 1. So at 0 and 360, cosine is 1. That's why at 0, we're 1, and at 360, we're 1. Cosine is 0 at 90 and 270. That's why it's hitting the axis at 90 and 270, and then cosine is negative 1 at 180. And again, we can graph the cosine curve just like we graph the sine curve. I can type in cosine x. No, cosine x, zoom 7. And it'll graph the cosine curve for me. And again, I could change my window if I want to just look at the 0 to 360 side. All right, but what we really want to talk about today is, to get you used to the trig graphs in general, but a couple of key features about trig graphs. Their amplitude, frequency, and period. So the standard trig graph, and using sine as example, is like y equals a sine bx. And the absolute value of the a, so the number in front, the absolute value of that is called amplitude. So let's experiment with that a little bit. So let me get in sine here. So sine x, and again, let me change the window to go from just 0 to 360. And so this is our standard sine graph. So this is just y equals sine x. Now notice that there's no number in front of sine, but we know there's like a 1 there that we don't write, so that's why it's, an amplitude of 1. But if we were to change this to, say, 3 sine x, what's going to happen is the amplitude of the graph is going to change to 3. And I think you'll quickly realize what amplitude is. It's basically the height of the wave. So it goes up to 3 and down to negative 3. So the number in front is basically the height of the wave. Now, why do we say absolute value of a is amplitude? Because even if we had a negative number there, so let me change that. Let's do negative 3 sine x. What happens when you have a negative there is the graph gets flipped upside down. So instead of going up and down, it's down then up. It's actually a reflection across the x-axis, and we've seen that before when we did transformations. But even though we're going down to negative 3, we are still going up to positive 3. So the amplitude is like how high does the graph go at any point. It's not necessarily the first place it goes. It's just what's the height of the graph at any point during the graph. So even when that number is negative, your amplitude is positive. Then the number after sine before x, the coefficient of sine x. Again, let me go back to just regular old sine x. Now this is a complete sine curve. It has the uphill, the downhill, starts at 0, ends at 0. This is a complete sine curve. But if I were changing from sine x to, say, sine 2x, our amplitude is not going to change. It's still going to be the same height. The frequency of the wave is going to change. And so what you see here is I get 2 complete waves. Here is 1 complete wave, 2 complete waves. So let me drag this over for a moment to help us out. So amplitude is height. Frequency is the number of waves. And when we calculate waves, we calculate it in a 0 to 2 pi interval, or a 0 to 360. From 0 to 360, how many waves do you have? And again, if we were to change this to be something like, say, sine, change that to 3x, we're going to see then 3 complete waves. There's 1 complete wave, 2 complete wave, 3 complete waves. And so that is what our frequency is. It's how many waves you have. And then lastly is period. And period's probably actually the most important of all of these. It's very helpful in solving the complicated ones. Period is where the first cycle or wave, let me call it wave because that's what I did on the last one. So it's where the first wave ends. So let me use this as an example that this would be 90 180, 270, and 360. Because I set my window to be 0 to 360. Now this was the graph y equals sine 2x. We have a period formula, 2 pi over b, super important. So to figure out your period, now like the number in front of sine, this is your amplitude, so that's our A, that's our amplitude, and this 2 is our we call it B, but it's our frequency. Period is not in here just like amplitude and frequency are. Period, you have to do a little formula. And so your period is 2 pi divided by the B term, which is your frequency. So 2 pi divided by the B term, 2 pi divided by 2, and I can simplify the 2 over 2 is simply 1 pi. And so the period is pi, and pi we know is the same thing as 180 in radians. And so what this is that's the location of where the first wave ended. So again, here's my first wave. It stopped at 180. That's what period is where the first cycle ends. But most importantly, we have a formula we need to memorize that's really, really important. It's something we'll add to our reference sheets and we'll talk a lot about. 2 pi over frequency, 2 pi over b. All right, how are we doing on time? Feel like I'm running a little late. Yep, we're at the 11.5-minute mark. Let me run through a couple of very, very quick examples because it's really the background that took time, but the questions are really, really quick. What is the amplitude of the graph? It's the number in the front, 2. Done. What is the period? Okay, the period is 2 pi divided by the b term, which is 2. 2 pi divided by 2 is pi. Done. I think we'll start in class there. So like I said, those were very, very quick examples. All right, see ya.